for example 1, we have a pulley with a radius r of 0.16 meters. It has a moment of inertia I of 0.380 kilograms per meter squared. And it rotates without slipping, so we know that there is no energy lost due to that. And there are 2 blocks attached to the pulley. We have a 4 kilogram block and a 2 kilogram block. The 4 kilogram block starts 5 meters from the ground, and the 2 kilogram block starts on the ground. So we want to know what the speed of the 4 kilogram block is going to be just before it hits the ground. So just based on kind of the information we've been given, we know that we're looking at a type of energy problem because we're looking at height and we're talking about speed. So those are good variables to indicate that we're talking about energy. We also know that we're talking about a pulley, so that would indicate that we're talking about some kind of rotational energy or rotational kinetic energy. So I will move this over to the whiteboard so that we can work on this problem. Again, make sure if you have any questions, you just say it in the chat, and I'll do my best to explain what I'm doing. Okay. Okay. So from this problem, we know that we have a pulley with a 4 kilogram block and a 2 kilogram block. The radius of the pulley we were given is 0.16 meters, 160. And the moment of inertia is 0.380. We also know that the 4 kilogram block starts above the ground at a height of 5 meters. So that is the information that we're given about this problem. Now we need to figure out how fast the 4 kilogram block is going to be when it hits the ground. So knowing that I'm talking about an energy problem, I can say that at the beginning of this problem, when nothing is moving, I do not have any kinetic energy. I don't have any elastic potential energy. The only thing that would be present is potential gravitational. It's not moving, there isn't a spring, so the only thing that can be present is due to gravity. So at the beginning of the problem, I have that. And at the end of the problem, if I'm looking at the scope of the 4 kilogram block, which I'm going to label as 4, I know that I'm looking for the speed just before it hits the ground, meaning that there shouldn't be any height at that point. So there should be no gravitational potential. And again, there is no elastic. So I can say that that would be equal to the kinetic energy of the 4 kilogram block at that point. So that's just using my conservation of energy equation. So let's break this down. So I know that at the beginning point of this problem, I have changed the pen color so you guys can see that. So let's look at what energy is present at the beginning of this problem. So we have the potential energy of the 4 kilogram box as it is off the ground. And we also have, so that would be equal to mgh, sorry. And that would be 4 kilograms times our 9.80 meters per second squared, times our height, which is 5 meters as we were given. And that would give us an energy of 196.2 joules. Okay, so that is the energy present at the beginning with the 4 kilogram block. As we know, nothing else is moving at the beginning of the problem, nothing else has height, so there is no other energy present, so this would be our initial energy. Now looking at the second half of the problem, we know that when the 4 kilogram block is on the ground, the 2 kilogram block must move with it. So the 2 kilogram block will have a height of 5 meters as well, meaning it will have potential energy at that final point. So the dark green is going to represent the energy after the block has hit the ground, and the blue is representing it at the initial point in the problem. So again, mgh is equal to 2 kilograms, 9.80 meters per second squared, and it will be at 5 meters, as we know that it must rise up as the other block lowers. So this will give us, it'll be a negative 5 meter change as the block will be going in the upwards direction, and we're going to call down positive for the 4 kilogram and up positive for the 2 kilogram. So that will give us a negative 98.1 joules. Okay, so we're getting closer to coming up with an answer for how much energy is actually in the system total. So looking at this now, we know that it starts with 196.2 joules of energy, and we know that 98.1 joules of that energy must be lost due to raising up P2, meaning that the kinetic energy in the second half of the system must be equal to 196.2 joules minus 98.1 joules, which will give us 98.1 joules total. So now we've removed the energy due to the movement of block 2. We are saying that 98.1 joules must go into the rest of the system. However, there should be some other energy present at that point. So we know that when the block hits the ground, it has no height, so there's no potential energy for block 4. But right before it hits the ground, everything in the system must be moving. So we should be looking at 3 forms of energy. There's the kinetic energy due to 4, the kinetic energy due to block 2, and the kinetic energy due to the pulley. So this is something that we haven't been talking about as much recently, but rotational kinetic energy is also a concept that we're going to be looking at in this problem. So at the beginning we have potential energy due to 4. Okay. So I am going to clear the whiteboard now so that we have more space to work. But the important part here is that we know that there's 98.1 joules of energy that is equal to the kinetic energy of our system. And we're going to do some math with that. Okay. Kinetic energy is equal to 98.1 joules. Okay. So as I said, there are 3 forms of kinetic energy. There's kinetic energy due to the pulley, which I'm going to call KEP, kinetic energy due to the 4 kilogram block, and kinetic energy due to the 2 kilogram block. So we're going to solve each of those individually. As we know, kinetic energy for a rotating object is equal to 1/2 I omega squared. This very closely matches our 1/2 mv squared that we use for translational kinetic energy. So that's an easy way of checking if you're on the right path for remembering your equation. So we're going to be using that. And 1/2 is equal to, we were given a value of I at the beginning of the problem, and that is equal to 0.380. So you will not have to solve for that in this problem. And omega, we don't necessarily have. But as we're solving for a value of velocity, I don't necessarily want to write omega as omega because that doesn't give me any information I want. So instead, I'm going to rewrite it as v over r squared. This is because I know that omega is equal to, v is equal to r omega. So I can say that omega is equal to v over r. This will give me more information that I want to know about the problem, as I know that every single component in this pulley system should be moving at the same speed. So that velocity is part of what I am solving for. So simplifying this into a decimal value, I get 7.4218 v squared, as I do not have an answer for that v yet, but I will get to that point. Okay. So that is the kinetic energy of the pulley. Now let's look at the kinetic energy of block 4. So block 4 is just moving in a linear motion, so we can go back to our regular kinetic energy equation, which is 1/2 mv squared. So 1/2 times 4, which is our mass we're given. And again, we don't have v, but we are solving for it. So we will simplify that to be 2v squared. I'm still leaving things in terms of variables, as I will be adding these kinetic energies together to equal 98.1, which will allow me to solve for v. But currently, I just need to know the relationship between velocity and kinetic energy. So lastly, kinetic energy of block 2 is exactly the same as block 1, as block 4. mv squared is equal to 1/2 times 2 times v squared, which will give us v squared. And as I was saying, the reason that we can make this assumption that v is what we're using and that all the v's are the same is that if you consider a pulley system, you can't have one object moving at a different speed than the rest. They're all moving at the same speed. That's why we can say that v, instead of labeling it velocity of the pulley, velocity of block 4, we can just say that it is velocity total. So these are my 3 kinetic energies, and I know that the sum of my kinetic energies should be equal to 98.1 joules. So I can add those together, and I can factor out that v squared. So 7.4218 plus 2 plus 1 is equal to 98.1. Okay. So again, just doing algebra at this point, I am left with a velocity of 3.1 meters per second. And that will be my final answer. So this really does come down to our conservation of energy concept. As long as I'm following along with that, I should be able to get to the right answer. We determined what energy was present at the beginning of the system. We determined the energy lost due to one block being lowered. We determined all of the kinetic energy present when this system is in movement or right before it hits the ground. And from there, we're able to calculate the velocity. So the new concept here is of the rotational kinetic energy. But as you can see, it's very similar to linear kinetic energy in the format of it and the information that you're given. So example number 2 here. Bhavdeep, do you want to explain that one?
Sure. So the second example talks about rotational kinematics and how that's related to guns, because that's an interesting topic at this point. It talks about how a rifle is a long gun whose barrel has been grooved or rifled with on the inside with spiral channels, which basically allows the bullet inside to rotate while it's coming out of the chamber. Um, Bullets fired from a rifle spin. That's kind of what they were trying to say. And the rest of the stuff is fun facts. So we'll just skip to the question real quick. So the question is: due to rifling, a bullet fired from an M16, which is a rifle, rotates 2.5 times on its journey from the breech to the muzzle, which is the end of the gun. And then it gives the barrel length of 510 millimeters and a muzzle velocity of 950 meters per second. Meters per second. We have to determine the average translational acceleration, the average angular acceleration, and the final angular velocity. So we're going to use our kinematic equations, and if you guys don't have any questions about the question, then I guess we should move on to the whiteboard and solve it. So let's just write down the given quantities first. We have our distance given to us as 510 millimeters. We also have been given an initial velocity of 0 because the bullet would be at rest. And we've been given a final velocity or a muzzle velocity of 950 meters per second. Clearly, if it travels that much distance or that little distance with that much speed, obviously the acceleration is really huge. Anyway, let's now find out our translational or linear acceleration. So in part A, we've got Well, we've already got these quantities and we need to find out acceleration. So this is the part that we've already covered in class before. And we can use our kinematic equations to find out the acceleration. Freya, would you like to suggest which kinematic equation we should use?
Well, just looking at the problem, I see that we have an initial velocity, a final velocity, and a distance. And I know that we want to solve for an acceleration. So I would say that the equation we want to use is that v squared is equal to v initial squared plus 2a delta, in this case, we're going to call it delta s.
Absolutely. So we can rearrange this equation then to find out the acceleration, where a will be equal to v squared over 2 delta s. And we do not account for v naught because it is 0. So it just kind of cancels out. When you put the quantities in, we get 950 over 2 times 0.150, um, 0.510, my bad.
Sorry, let me erase that. Okay.
And the reason it's 0.510 is because we converted our millimeters to meters. It was relatively intrinsic this time around. And the final answer we will get because of that then will be 8.8 times 10 to the fifth meters per second square. Clearly a huge quantity. Um, okay, cool. All right, I'll probably take questions at the end, but if nobody has any questions about that, we're going to move on to part B then. And part B was trying to calculate the radial acceleration or the angular acceleration, my bad, which was alpha. So we essentially use everything that's been given to us. However, we will need for most kinematic equations either angular velocity, which we don't have and we really don't want to find at this point, or time. And time would be much easier to find with the quantities that we've been given. So let's try to find out the time. To find out the time, we have the velocity, the distance, and we can obviously consider that using the average velocity formulas, we can figure out an equation for time. So we could say that v bar, which would be the average velocity, um, would be equal to delta s over delta t, which would be the change in the distance over the change in the time. It was at the same time also equal v plus v naught over 2, which would be the summation of both the velocities divided by 2, a general average mean formula, if you will. And v naught in this case would again be 0, so we do not account for it. And we can rearrange the equation further to find out a value for delta t. Delta t would equal t because, again, the lower limit, which would be t final minus t initial, we're considering t initial to be 0. So that would be 2 delta s over v plus v naught. And that would equal, after putting in the numbers, 2 times 0.510 over 950, which would equal approximately 1.074 times 10 to the negative third seconds.
And the reason we were able to determine that time was what we were solving for is because time is something that we can relate between angular and linear motion, right?
Absolutely, that's one quantity that won't change over both the motions.
Okay, so that was a very logical path to take. Okay.
Certainly. So would we want to then clear the whiteboard so that we can move on to the next part? Well, not the next part particularly, but now that we have the time, we can actually go on to the angular motion rather than the linear motion. Do we have any questions so far? Well, I'll take that as a no.
So as we solved from the last part, we know that t is equal to 1.074 times 10 to the negative third seconds.
Absolutely. Thank you. And we have, all right, so now considering the angular motion, we now have to consider how many times the bullet rotates, first of all. So it's been given that the bullet rotates about 2.5 times, which means that we have our theta in terms of rotations, and we need to convert that into radians. The simple formula is just to generally say that one rotation is equal to 2 pi. So we can deduce that two rotations would be 4 pi, and then a 0.5 rotations would be 5 pi rotations, or radians, my bad. And that's not that difficult. In addition, since the bullet is in the chamber and it's at rest before it's being fired, hopefully, we can say that our omega naught, which would be the initial, would be our 0 radians per second. In addition, now we also have delta t, which is, or t in this case, which would be 1.074 times 10 to the negative third. We've been given that. So we could now use an equation from rotational kinematics in order to solve for alpha, which would be our rotational acceleration, if you will. Freya, did you have any thoughts on which equation we should use?
So thinking in terms of what we're given, we have an initial angular velocity, we have a distance, we have time. So I think that we're looking at our delta theta is equal to omega t plus 1/2 alpha t squared, which is very similar to our linear equation of delta x is equal to v initial t plus 1/2 at squared. So that's a comparison I can make.
Absolutely, I think that's a very logical approach. And since we've been given everything, as you said, it would be the right thing to do, in my opinion, at least. So rearranging the quantities once again, we can get an expression for alpha, which would be 2 theta over delta t squared, or t squared. And when we put in the figures, we get 2 times 5 pi divided by the very small time number squared. So 1.074 times 10 to the negative 3 whole squared. And then using our laws of exponents, life becomes a little easy, and the final answer we get would be 2.7 times 10 to the 7 radians per second. Alrighty. Did anybody have any questions on that? Did we explain that okay?
So as you said, we were expecting a quite large acceleration, partially just using the logic that it's a bullet, partially given the fact that it's speeding up so quickly. So does this match kind of the answer that we would expect from this problem?
Definitely, I think we had a pretty big quantity for the translational acceleration as well, and for the rotational acceleration. Um, so it would definitely make sense to um, get these quantities, or at least large quantities at the end of the day. In addition, we also got a very small value for time, which was about 0.001704 seconds, which is pretty small when one considers when a gun is fired. Sure, it might take that less time for a bullet to escape the chamber. So I believe the values that we wanted are more or less correct, and we can move on to the next part if nobody has any questions. Do you want to clear the whiteboard so that we can move on to part C?
Yeah.
Alrighty, so we've been given our time, we have our rotational acceleration at this point, and we need to find out the angular velocity. We can again and we've been given that the bullet is at rest initially, so the initial angular velocity is 0. So we need to find out the final angular velocity of the bullet when it escapes the muzzle, if you will. So we have another rotational kinematic equation. We can say that omega equals omega naught plus alpha delta t, which is which is similar to v equals v naught plus at. And when we put in the values, just a general amount of value putting, we get 0 plus 2.7 times 10 to the 7th times 1.074 times 10 to the negative 3, which comes round about to about 4700 radians per second. And that we could also consider pretty high. It's a really fast bullet, this one, and it's rotating at a very fast speed as well because the grooves in the rifle. Um, does anybody have any questions regarding A, B, or C, or did Freya, did you have anything to add to these problems?
I just think it's important to note that if you're having some confusion about your kinematic rotational equations, you can see that the format very closely matches that of the linear equations. You're just replacing your linear values with angular values. So velocity becomes omega, acceleration becomes alpha, things like that. So if you do remember one set of equations but not the next, you can usually come up with the other equations.
Certainly, that's good insight. And if nobody has any questions, then I believe we can move on to the next one.
So in this problem, we're looking at torque. So we have a bridge of, the bridge itself has a mass of 18,000 kilograms. And we have a car of mass 30,000 kilograms. And as we know, a car would be very heavy, so that makes sense. We should be looking for heavy values for that. The bridge itself has a length of 40 meters, and the car is parked about 10 meters from the top of the bridge. So while the bridge is being raised up at a 30-degree angle, we want to find the tension in the wire that's pulling it upwards. So it's being pulled upwards, we want to figure out what the tension is. So we're going to look at all the forces that are present, determine the torques, and figure out what the missing force is. So I will set up the whiteboard and we'll get started. Okay, so the information that we have about this problem is that the bridge is being raised up at a 30-degree angle with a car on it, and that the car is 10 meters from the top of the bridge. We also know that the tension is at an angle of 70 degrees from the bridge. So I'll write that there. The mass of the car, which I'm going to call little m, is 30,000 kilograms. And the mass of the bridge, which I'm going to call big M, is 18,000 kilograms. We also know that the length of the bridge is 40 meters, sorry. Okay. So given this information, there's a couple of conceptual things that we need to understand. So Bhavdeep, looking at the situation, what do you think the sum of the torques would be equal to?
Looking at the situation, the sum of the torques should be equal to 0, primarily because it doesn't seem to be moving particularly, well, it doesn't seem to be rotating particularly, so it's a relatively linear system, at least
Exactly.
in 2 dimensions.
So a non-moving object, an object that's stable, should be in something called static equilibrium, meaning that we can assume that the sum of all of the torques in the system is equal to 0. We also know that our torque equation is our force, is our radius cross product with our force. It can also be considered our radius times our force that is perpendicular to the radius. So we can talk about that a little bit more when we calculate. And yeah, so those are the concepts that are important. So let's look a little bit more at what is actually acting on the system. So I'm going to calculate my torque from our initial point here. And just a reminder, our little m here is the mass of the car, and our big M is the mass of the bridge. So we will be using those in the problem when we do our math. So I'm going to call my point r equals 0. Basically, my initial point from which I'm calculating my torque is going to be the bottom of the bridge. And let's look at what torque is present. So I assume that the cable provides a torque, so I'm going to call that the torque due to the tension. And it looks like the car would provide a torque, so I'm going to call that the torque due to the car. Bhavdeep, can you see anything else that might provide a torque in this problem?
I need to close the equation first. There might be the tension, if you will, that's causing the torque.
So there's the torque due to the tension and the torque due to the car.
Oh, whoops, that is the tension, my bad.
But I believe that as the bridge has a mass, would it also have a tension? I would also have a torque, I mean?
Oh, certainly, yeah. That would be the torque due to the bridge.
So those are the three that I can identify. There doesn't seem to be any other torques acting on the bridge. So I will be calculating for those, but before we calculate, let's have a look at if those values would be negative or positive. So using our sign convention, we know that counterclockwise is positive and clockwise is negative. So the torque due to the tension is pulling the bridge upwards, which is in a counterclockwise motion. So I'm going to call that positive. The torque due to the car and the torque due to the bridge are both masses, meaning that they should be pulling the bridge downwards. So that would pull it in a clockwise motion, so I'm going to say that those are both negative. Do you agree with that, Bhavdeep?
Yeah, I would agree with that, Freya, although I think you lagged out there in the middle, so could you repeat it?
Okay. So yes, looking at our positive and negative sign conventions, we know that the forces that are pulling the bridge upwards, such as the tension, should be pulling it in a counterclockwise motion, so those will be positive. Whereas forces like the mass, which are negative, which are pulling the bridge downwards, will pull it in a clockwise motion, so those will be negative. So those will be how we assign our positive and negative values. So let's look at this now. We'll take it one torque at a time. We have the torque due to the tension, and the radius in this case will be the distance from my initial point, which I set at the bottom of the bridge, which is down here, to the point where the tension is acting. And that is going to be at the top of the bridge. And that will give me 40 meters, as I know that is the length of the bridge. Now, as far as my force, I know that tension is what the force is, but I want the perpendicular part of that force. So if I know that it's acting at 70 degrees, then I know that the perpendicular part of that force is the sine of 70. Yeah, because it will have components. So we have our x component and we have our y component. That y component is going to be the part that's perpendicular to the bridge, and that will be the sine of 70 degrees. So I have my radius and I have my perpendicular force, which, as I know, are my two aspects of my torque equation. So that is the torque of the truck. That gives me my answer for that. Now looking at the torque of that's the torque due to the tension. Now looking at the torque of the car, I have said that this will be negative, so I'm going to assign a negative sign. I know that the force will be equal to mg, as I know that that is the force pulling it downwards. But let's look at the distance first. So I have said that the car is parked 10 meters from the top, so I'm looking at the distance from my initial point to the 10 meters below the top. So that will give me 30 meters. And I'm looking at 30 meters. My force is going to be mg, so 30,000 kilograms times 9.80 times. And do you think I'm looking at the sine of theta here or the cosine of theta when I'm talking about the perpendicular force, Bhavdeep?
You're looking at the sine because, well, the sine is perpendicular over hypotenuse. So according to the torque equation, if it's RF sine theta, you're looking at, well, if it's perpendicular, then it will be RF sine theta.
Okay, so just looking at kind of my gravity force that's acting on the bridge and where the angle would be, I can say that it is either the sine of 60 or the cosine of 30 degrees when I'm looking at that perpendicular one. So I'm going to say sine of 60 degrees. And this is just worked out through geometry. And that would be my torque due to the car. So I'm going to clear the whiteboard so that we can have space for the last torque, which is the torque due to the bridge. So kind of putting this together now, I have the sum of the torques is equal to my positive t sine of 70 degrees, which we calculated, times 40 meters, minus my 30,000 kilograms, 30,000 times 9.8 times sine of 60, and that is times 30 meters. And we're going to subtract our last force, which is going to be very similar to the force due to the car, but rather than using 30,000, we're going to be using 18,000, as that is the mass of the bridge. Again, we're looking at mg, so that's 9.8. And again, it will be acting at the same angle, as we know that gravity acts directly downwards, sine of 60. However, as we know, when we have a uniform object, we can consider that all of its mass is acting at the center of mass. So for a 40 millimeter bridge, we're going to be looking at half of that. So we're going to be looking at the middle point, so 40 over 2, which will give us 20 meters. And again, we said that the sum of all of our torques should be equal to 0. So we have our torque due to the tension, our torque due to the car, and our torque due to the bridge. And we are adding or subtracting depending on whether they are acting clockwise or counterclockwise, and it should be equal to 0. So using our algebra rearranging, we end up with a tension value of 285,000 newtons, or 285 kilonewtons. And does this kind of large value make sense, Bhavdeep?
Absolutely. The mass of the bridge is comparatively relatively less to the mass of the car, so there will be a lot of tension in the strings in order to, or yeah, in the cables in order to hold the bridge up, else everything would collapse.
Okay. So yeah, we were looking for a very big value there, so that seems to indicate that we're on the right track, and that would be our final answer for the question. So the key concepts here are understanding the sign conventions of counterclockwise and clockwise, and understanding that you're looking at a distance, which is going to be along the object, and a perpendicular force. So make sure you understand that, the idea of calculating the perpendicular force.
Example 4 talks about the different kinds of accelerations. In this, we have a wheel of diameter of 40 centimeters, which starts from rest and rotates with a constant angular acceleration of 3 radians per second, per second square. We need to compute the radial acceleration of a point on the rim for the instant the wheel completes its second revolution. That's a hint. From the relationship, radial acceleration equals omega square r, and the radial acceleration equals v squared by r. So we will also be talking about a little bit about translation acceleration, hopefully, and we'll see where that goes. However, let's go on to the problem, if there is no questions about the problem. Doesn't seem to be. So let's go to the whiteboard and solve it. Alrighty, well, we've been given a couple of things. We've been given the radius as 50 centimeters, sorry, the diameter as 50 centimeters, and we've been given alpha in this case, which is about 2 radians per second. All right. We also know that the thing starts from rest, so omega naught would be equal to 0, particle, if you will. There we go. And we have, well, we pretty much have everything at this point to use a kinematic equation or rotational kinematic equation. Freya, would you like to suggest which one?
So looking at the problem, we know that we're solving for omega. That's what we want to find. And we have omega initial, but we also have alpha, and um, we have a way of figuring out kind of what distance might be traveled per revolution. So I believe that we could use our omega squared is equal to omega initial squared plus 2 alpha delta theta.
Absolutely. And as you mentioned, we have a way to find out what delta theta in this case would be. We've been given that it goes through 2 revolutions before we need to calculate anything. So we can say that a delta theta would be 2 revolutions, which again, due to a conversion, would then become 4 pi radians. Just as a reminder while we're doing that, 1 revolution equals 2 pi, as a 2 would be 4 pi, and so on. Half a revolution is about pi radians. Okay, moving on. We have, well, we can now put all these values in our equation and find out a value for omega. And the only reason we're doing that is because we need to find out omega for our first um, kind of equation, which was radial acceleration equals r omega squared. Um, so let's find out omega and then put that into the equation.
So what you're saying is we were given an equation which is radial acceleration is equal to r omega squared, right? And we're solving for the omega in this part of the equation.
Absolutely.
Okay. So going back to our equation over here, our kinematic equation.
Alrighty, and then we can just solve for omega, which would be under root of 50.24. Which comes out to be about 7.088, or for the sake of convenience, 7.09 radians per second. Alrighty. Now that we have our omega, we can actually put that into the formula that we mentioned above. So let's put that in, and we get alpha radial or radial acceleration equals r omega squared. We aren't directly given the radius, but we could definitely consider it as 50 centimeters over 2 times 10 to the negative third, which could, 10 to the negative second, which would be converting it into meters as well.
Okay, so we could say that's 0.50 divided by 2.
And then omega squared, which would be 7.09 squared. And when we get the result for this, we get 12.6 radians per second squared, which gives us our radial acceleration in terms of when it's rotating at that particular, well, when it has completed 2 rotations with that particular velocity, angularly. Does anybody have any questions about this part, or should we move on to the next one? Did you have anything to add, Freya?
So this answers part A of the question. I'd say that the most important part of this is just understanding the equations and how they can be used with the given information. And as you can see, converting from diameter to radius, converting from revolutions to radians, things like that, small conversions are a big difference between getting the problem right and wrong.
Certainly, attention to detail is pretty much the most important thing in physics. Absolutely. And since we do not have any questions, I believe we can definitely go on to the next part. and find out, say, the linear radial acceleration, if that's ever a thing.
Okay.
So in this case, we basically can consider radial acceleration to be v squared over r, therefore need to calculate the v. And this would be radial acceleration, as you might remember from your Newton's laws or motion in a vertical circle, where we write the sum of forces equals mv squared by r, which would definitely say that the acceleration in a circle radially or on this over the circumference is v squared by r. And that's why we need to calculate v in this case. So to calculate v, we have a formula of omega r. And then since we found our omega in the previous question, we can just throw that in. Oh, sorry, my bad.
Sorry. So the equation that we are using, sorry, just to clarify, is that a radial is equal to v squared over r, as we've been given before. But in order to use this, we need to solve for v, which we don't have yet, but we can solve for using our v equals omega r equation. And omega, as we know from the last problem, is equal to 7.09. Okay.
Absolutely. Thank you. And we can just essentially just throw this in along with our radius that we also calculated from the previous equation. And that gives us 7.09 times 0.50 over 2. And when we throw it in, we get an answer of about 1.77 meters per second. The radians kind of gets canceled out because of our nice little radius there, essentially. Or not canceled out, but something happens in there. And we have 1.77 meters per second as the velocity. Now we can just throw that into the other formula and then get our answer. So we have 1.77 over a radial equals 1.77 over, again, the radius, which is 0.250. And the answer we get then is about 12.3 meters per second square. So at the end of the day, using our quantities, using our given quantities, we found radial acceleration in terms of radians per second. We also found out the radial acceleration in terms of meters per second. So we found it in terms of how our angular motion is and in terms of how linear motion is as well. If anybody has any questions about parts A and B, now would be a wonderful time to ask, or about pretty much any questions, because I think that was the last one. And if not, then Freya, if you had any other comments, I would definitely appreciate it.
So again, with this part of the problem and with pretty much every problem we went over today, you can see that it really falls on how well you know the equations and understanding how to get the variables to fill in your equations. So kind of starting from an equation, knowing what you need to solve for is a good way of getting started on any problem.
Definitely. Even though some professors might give formula sheets, just going back and forth and trying to figure it out will definitely confuse you more than it's supposed to.